Well, we'll start with a thought for the day. Some people have no idea what they're doing, and a lot of them are really good at it. This is George Carlin, who was a comedian, and but there's a lot of truth to this, I think. A lot of people don't know what they're doing. They try to go through the motions and just be like, I'll try to mimic what we've done. I really want to encourage you. Make sure you understand the processes. Why are we doing things? What's our goal? If you don't understand what the goal is and why we're doing things, you can definitely fill up a lot of time and you can fill up a lot of paper, but it doesn't mean you're making a lot of progress in solving the problems. But know this, you are capable. I've seen it. You can do it. Now, where are we going today? We're going to do a little bit more with Gauss-Jordan and talk a little bit about applications and what we mean by that. But then we're going to start talking about matrices and doing some very basic arithmetic with matrices. And for today, we're going to talk about some very simple things. If I want to compare two matrices and ask, are these the same? If I want to add two matrices or subtract a matrix from another matrix, I want to scale. The mantra is work entry by entry. So you're just going to do the operation to every single individual entry of the matrix. So that's today. All right. Well, what do we mean when we talk about applications? To be clear, the whole purpose of Gauss-Jordan elimination is to solve systems of what are known as linear equations. What's a linear equation? We have a collection of variables, and we're going to have possibly many variables. So we've run out of letters near the end of the alphabet, X, Y, Z. You know, what do we do when we need another letter? So that's when we start using subscripts, X1, X2, X3, and so forth. So those are our variables. In other words, those are our unknowns. And we have an equation, some constant times the first variable, some constant times the second variable, so forth and so on, up to some constant times the last, equals a number. We call these linear equations. Now you might think, okay, linear, line, and not a bad thought, right? Because if you think about the special case when we have two unknowns, that's the general form for a line, generic expression for a line. AX plus BY equals C. Now you might say, well, wait, what happens if we have more equations? Well, or rather, not more equations, but more unknowns. If you have three unknowns, what you have is not a line. What you have is a plane. And you can think of a plane like a flat piece of paper. And you can tilt it much like you could have lines with different slopes. And of course, you might say with more variables, oh, okay, higher dimensional analogs. The important thing is that when we say linear, you should just think, oh, that means a flat thing. That's what we mean by linear. And why do we like flat things? Because we know how to solve problems. That's why we like flat things. All right. So the main part of an application comes from setting up the system of equations. We solve by Gauss-Jordan elimination, which we've been practicing by name from the last lecture, but we're kind of doing it already before then. And then we have to interpret our solutions, if there's any. Now, there's a couple things that can happen. The ideal situation is we find one solution. And in terms of Gauss-Jordan elimination, what does that look like? Well, to the left of your divider line, because remember we're working with augmented matrices, so there's this line, it looks like almost all zeros except you have a string of ones forming a diagonal all the way down to the line. And from this, we say, aha, we can read off the solutions. The first variable equals B1. The second variable equals b2, all the way to the last variable. Now, it's possible you might have some extra rows of zeros. Those are redundant. But the point is, every single variable has one and only one number it's associated with. That's the ideal scenario. It's also possible that we have no solution. Now, that can happen if we get to the case when we have all zeros, and the only one, because every line that has a non-zero, the first entry has to be 1. That 1 is on the right-hand side of the dividing line. Why is this bad? Well, if you read off the equation, the left-hand side says 0, the dividing line is like an equals, and then you got the 1. 0 equals 1. Ha, nonsense, can't happen. No solution. Hopefully we won't run into any of those. Now, the last case is that we have some columns which are associated with a variable which don't have a first one in a row. So I've written down sort of a more explicit example. So when I talk about the first one in a row, you can see that in the first row it's the first entry, in the second row it's this third entry, and in the third row it's this fourth entry. Those are what I mean by the first one of the row. Now for those, you have to knock out all the other entries in that column. But there's 2 columns left over. Now, what does that mean? Well, it means that the variables associated with those columns, because each column comes attached to a variable, those are free choices. We can let them be whatever we want them to be. So that's why we have many solutions. Now I put many with a question mark because perhaps there's some other constraints floating around. One thing that frequently happens is that we're in a problem when we come back to our application where these variables represent quantities that can't be negative. You can't manufacture a negative number of cars. It's not like you run around and start bashing cars up at night. There's certain things that can't happen. And so that gives you some additional constraints which might limit how many solutions there are. But generically speaking, when you get this situation, you have multiple choices, and you have to explore what that means. So that's the idea. Any questions before we try doing an application? All right. So, this one's from the book. I haven't tried it yet. I hope it has nice numbers. Find the values A, B, C, so that the graph of y equals ax squared plus bx plus c passes through, and we have 3 points, -1, -5, 2, 7, and 5, 1. Now, this feels kind of familiar. We've done problems where we said, hey, how about we give 2 points and we find the line that passes through 2 points. Now, we're saying, well, we'll have 3 points. So we have -1, -5. That's probably from somewhere around there, 2, 7, somewhere around there, and 5, 1. So we have these 3 points. And we're trying to find a formula that looks like y equals ax squared plus bx plus c. What does y equals ax squared plus bx plus c look like, by the way? Have we seen anything that looks like that before? It's a parabola. So this, we've talked about parabolas. So we're trying to find the parabola that passes through those 3 points. Now, is that possible? Well, this thinks it's possible. And I'll go ahead and tell you that as long as your x values are distinct, it will be possible. It's always possible to find something in the form ax squared plus bx plus c that passes through any 3 points, all of them with distinct x values. You can't have 2 points with the same x value because then you couldn't have a function. We have that vertical line test. All right, so what's the goal? Well, step 1, we need to set up a system of equations. Right now, we don't have a system of equations. We have a formula that we're trying to find, but we also need to make sure we have a linear system. All right, and in particular, as we look at it, since we're finding A, B, C, we're trying to set up formulas that involve what we're looking for. So we want to find formulas with A, B, C as the unknowns. So what can we do? What can we do? Any suggestions, ideas, things to try? I would say a bad strategy is randomly guess A, B, and C, because there's a lot of possibilities. Well, what do we have? We have points. Oh, and by the way, maybe before I get too far, if I'm solving for 3 unknowns, how many equations would I like to make? 3. Now, usually when you're solving for 3 unknowns, you want 3 equations. Well, what do we have 3 of? We have 3 points. So what we can do is we can turn the points into equations. So here's a point, -1, -5. Well, what can we do with it? It has to be a point on this curve. We plug it in. So where we see the y, well, that's going to be our -5. And I'll put that on the other side in a second. And then we put in for x, -1. So you get a times -1 squared, which is a, b times -1, which is -b, and plus c, and that has to be the y value, -5. Well, okay, good. Then we have another point, 2, 7. Repeat the process. So for the point 2, 7, throw it into the equation. Everywhere we see the x's, we put 2. Everywhere we see the y, we put the 7. So a times 2 squared, 4a. That's right, it's a 4a into this problem. B times 2 is 2b. Or perhaps it's not 2b. That is the question. No, it's 2b. And y is 7. All right. And now we do the last point, 5, 1. All right, so for 5, 1, what does that give? Bigger numbers. 5 squared, 25. Ugh. And then 5b and plus c, and that equals 1. But now we're in good shape. We have what we wanted. 3 equations, 3 unknowns. They're the good kind of equations in that they're linear. They involve A, B, and C. So it's up to us to solve it. Well, we turn this, and we're going to do some Gauss-Jordan elimination. So we write down our coefficients in our augmented matrix. And so we have 1, -1, 1, -5, 4, 2, 1, 7, 25, 5, 1, 1. All right. Now, we're going to practice Gauss-Jordan elimination. And so we'll just go through the idea. We work in the first column at a time. We say we'd like that first entry in the first column to be a 1. Whew, success. All right, well that saved us a step. Now we want to knock things out. And so we're going to do 2 rows at once. We're going to take -4 times the first row, add it to the second row, -25 times the first row, and add it to the third row. So in particular, if we use our notation, minus 4 row 1 plus row 2 is going to become the new row 2, minus 25 row 1 plus row 3 is going to become the new row 3. Okay, so if we do that, we haven't changed the first row. Next up, we say, well, minus 4 times the first plus the second. Minus 4 plus 4, 0. Minus 4 times minus 1 is 4, plus 2, 6. Minus 4 times 1 is minus 4, plus 1, negative 3. Minus 4 times minus 5 is 20, plus 7, 27. All right, that's the operation minus 4 row 1 plus row 2 goes to row 2. Now, the bigger numbers. Minus 25 plus 25, 0. Well, that one's not surprising. Here we get 25 plus 5, 30. Then we'll get minus 25 plus 1, minus 24. And then we'll get 25 times 5, the negatives cancel. That's 125 plus 1 makes a number, 126. Okay, good. Well, hopefully good. All right, now we're allowed to clean up. And simplifying sometimes gets a bad reputation. I had to give a talk to my calculus class recently, like, don't be afraid of simplifying. Simplifying is your friend. So before we do the next step, is there anything we can do to make some of these rows look nicer? I know it's a vague question. We can scale. Looking at the second row, 6, negative 3, and 27, does anything divide into all those simultaneously? 3. So we can go ahead and scale that by 1/3. So that would be 1/3 row 2 becomes row 2. All right. At the third row, does anything divide into 30, 24, and 126? One's maybe a little bit harder to do in your head, but there's a nice number that does that. 6. So I'll go ahead and scale that, just so we have slightly smaller numbers. Smaller numbers, turn out, are easier for us to understand. Maybe not easier for us to understand, but they're easier for us to work with. So I'm just scaling everything down. Scaling the second row by 3, the third row by 6, and 6 divides into 126 21 times. All right. So now we're happy with column 2. We have that one. We like that one. We're going to keep that one. So now we come to the second column, and we see we have some non-zeros. So we say, okay, our next goal is to work with that 2. And I know we just scaled down, but we get to scale again. Because we don't want the 2. What do we want? We want the 1. Okay, so we'll scale again. All right, so scale by a factor of 1/2 to get the 1. And if we do that, 1 minus 1, 1, minus 5, 0, 1, minus 1/2, 9 halves, and 0, 5, minus 4, 21. All right. Now, using our 1, Gauss-Jordan elimination says, clean up that rest of that column. So I want to make the other entries besides that middle 1 to be 0. So we can add 1 times the second row to the first row, and then multiply the second row by 2. So multiply negative 5, add to the third row. So in our notation, row 2 plus row 1 becomes row 1. and minus 5, row 2, plus row 3 becomes row 3. All right. What will we get? Well, the middle row is as is. 0, 1, minus a half, 9 halves. So for the top row, we're just adding the second row to the first row. 0 plus 1, 1. 1 plus negative 1, 0. Negative a half plus 1, a half. 9 halves minus 5. Well, minus 5 is minus 10 halves. So 9 halves minus 10 halves minus a half. Okay, now the other operation. 0 plus 0, 0. Minus 5 plus 5, 0. So I'm multiplying by negative 5 and then adding. So it'd be 5 halves minus 4. 5 halves minus 4 is the same as 5 halves minus 8 halves. So that's minus 3 halves. Minus 45 halves. Okay. Minus 45 halves plus 21. 21 is 42 halves. Minus 45 halves plus 42 halves minus 3 halves. All right. Well, good. Now we're happy with the first and the second column. We come to our final column. We say, all right, we have to make that entry, that minus 3 halves, a 1. Well, what do we do?
Multiply by the reciprocal and negative.
Yeah, multiply by minus 2/3. Minus 2/3, row 3, becomes row 3. All right, so we have 1, 0, a half, minus a half, 0, 1, minus a half, 9 halves, 0, 0, 1, 1. Okay, so using that 1, we need to knock out the other entries in the column. Okay, so we'll say if I add 1/2 times the third row to the second row, that'll knock out that minus a half entry. Then if we take minus a half times the third row plus the first row, that'll knock out that half entry. And so in notation, if we take 1/2 row 3 plus row 2, that becomes row 2. And minus a half row 3 plus row 1, that becomes row 1. Giving us the following. Okay, the last row is as we want it. 0, 0, 1, 1. Let's do the second row. We're multiplying the third row by half and adding up. It's 0 plus 0, 0. 0 plus 1, 1. And because these two zeros, they're actually not going to affect the two columns. That's the good news. We want that. We really are trying to knock out lots of entries. A half minus a half, 0. So now we have a half plus 9 halves. A half plus 9 halves is 10 halves, also known as 5. All right. First row, 0 plus 1, 1. 0 plus 0, 0. Now we have to pay attention. Minus a half plus a half, 0. Minus a half, minus a half, minus 1. All right, so now we have to read off our answer. Remember, each column is associated with the variable. So the first column was our A column. The second column was our B column. And the third was our C. So we read off A is minus 1. B is 5. And C is 1. Or y equals, now that we have a, b, c, minus x squared plus 5x plus 1. Is there a way we could check our answer? Yes, because we have the 3 points. If we plugged in minus 1, minus 1 squared is a 1. So we have a minus 1. This will become a minus 5. This will become a plus 1. All together gives us negative 5. Plug in 2. Minus 4 plus 10 plus 1. That's going to be 11 minus 4, which is 7. Plug in 5. Minus 25 plus 25 plus 1. This is the 1. So we did it right. All right, good. Any questions there? Okay. We'll go through the next one a little bit faster, because hopefully we're really good at this Gauss-Jordan elimination. A large company wants to lease 12 airplanes, which will have a combined capacity of 220 passengers. And planes have 3 models. So there's 3 different types of planes. So version A, or model A, it can carry 10 passengers, and it costs $8,000 a month for the lease. Version B carries 15 passengers, and it costs $14,000 a month. And version C carries 20 passengers, and it costs $16,000 a month. What combination of planes will minimize the cost per month? That's what we want to build up to. All right. But there's sort of an intermediate step. We're not going to get quite exactly to the question we want in the first stage, because this notion of minimize, that's something we're not yet ready for right now. We can't jump right there. Because minimizing says you're trying to make something big or small. We're trying to say what's possible. Don't worry, we'll get there in a second. We will answer this question in the next 10, 15 minutes. I want to focus on 2 facts. We have 12 airplanes, and we have 220 passengers. So let's focus on that. So we have 12 airplanes that we want, and we want to have 220 passengers. So let's figure out what that tells us. Well, we have 3 models, right? So that means there's 3 choices to make. So I can pick how many of A, how many of B, and how many of C. So I'm going to go ahead and just use what we have for the symbol. So I'm going to let A, B, and C represent how many of each plane we're trying to get. So in terms of A, B, and C, this requirement that we have 12 airplanes, how can we write that as an equation? So remember what I mean here. A is the number of airplanes of type A. I'm going to use B to represent the number of airplanes of type B, C the number of airplanes of type C. The fact that we need 12 airplanes, what equation does that become? A plus B plus C equals 12. Okay. We need 220 passengers. Again, in terms of A, B, and C, what does that become? Well, how much can plane A carry, or type A carry? 10. So I can carry 10A passengers with the planes that are of type A. Type B, well, similar, 15B. And type C, 20C. And that equals 220. So now I have my 2 equations. The cost, we'll get to that in a few minutes. That's not something equals something, right? Because you're trying to minimize, so that's why it's a separate question. I want to focus just on this. Notice the second equation everything is a multiple of 5. So let's go ahead, before we get into it, we'll write it as a plus b plus c equals 12. If we divide by 5, 2a, 3b, 4c equals a number 44. All right. Well, we do want to do our practice with our Gauss-Jordan elimination. 1, 1, 1, 12. 2, 3, 4, 44. You should, at this point, say, we don't have enough equations. Well, we don't have enough equations to find a unique answer. This often happens in reality, right? There's oftentimes lots of choices that we make, and there's flexibility. And so for right now, we're not going to stress that we have too few equations, but really what this means, we anticipate this means, is there's potentially multiple solutions that will work for us. In other words, multiple combinations of planes that will do what we need. All right, so in the spirit of Gauss-Jordan elimination, we say, okay, work in the first column, and in particular, we already like the 1, so we want to knock out the 2. So we're going to multiply the first row by -2 and add down. So -2 row 1 plus row 2 becomes our new row 2. So we get 1, 1, 1, 12, and then -2 plus 2 is 0, -2 plus 3, 1, -2 plus 4, 2, -24 plus 44, 20. You say, great, that was a great first column. But we're not done. We have more columns yet to work on. So we get to our second column, say, hello, second column, you look wonderful today. First, we want to make you a 1. You're already a 1. That's perfect. It's almost like they wanted this problem to be able to be done in a short amount of time. All right. So we're going to use that 1 to knock out the 1 above it. So we're going to take -1 times the second row, add it to the first row. So -1 row 2 plus row 1 becomes our new row 1. So this gets us to the bottom row, 0, 1, 2, 20, and then the top row, 0 plus 1 is 1, -1 plus 1, 0, -2 plus 1 is -1, and then -20 plus 12 is -8. All right. Now, at this stage, what's our next part of Gauss-Jordan elimination? The answer is, there is no more Gauss-Jordan elimination. This is it. This is what we called last time reduced. Every first non-zero entry is a 1. Every entry either above or below that 1 is a 0. We have done Gauss-Jordan elimination. We're over. But there's a catch here. What do you see? There's this extra column. Now, when you see this extra column, remember, what does that tell us? It really says, hey, this is like a free choice. So, the free choice is attached to C. So we're going to give it a name. I'm going to call it T for a moment here. So C, I'm temporarily calling T. Let's read off our equations. The first equation says A minus C, but I've given it a temporary name, minus T, is -8. The second equation says B plus 2T equals 20. And, of course, we also said C equals T. Or we can rewrite this in the following way. We want A to be -8 plus T. We want B to be 20 minus 2T. We want C to be T. How many solutions does that give us? If we weren't worried at all about where these came from, if we ignored the problem, how many solutions do we have? Infinitely many. I just pick a value for t, life is good. But then we remember, hey, this represents something. So I don't have infinitely many, so I got to pull that number back a bit. We start thinking, well, A, B, and C represent planes. Can we have a negative number of planes? No. Can we have a fraction of a plane? It's like, I just want a wing. No, it's not like chicken, right? You can't just ask for that. You got to have a whole number of planes. Now, with that in mind, one thing we can observe is, hey, we need A to be greater than or equal to 0, B to be greater than or equal to 0, and C needs to be greater than or equal to 0. And the other thing is t must be a whole number. Because if t is not a whole number, then we get fractions. Let's see what this says. If negative a plus t is greater than or equal to 0, what does that tell us about our value for t? So negative 8 plus t is greater than or equal to 0. That tells us what? T must be greater than or equal to 8. All right. We also have 20 minus 2t is greater than or equal to 0. What does that tell us? If we move stuff around, what does that give us? T is less than or equal to 10, right? Because I could add 2t and I could divide by 2. We also have that t must be greater than or equal to 0. Well, that really doesn't give us anything new. We already said t is greater than or equal to 8. So can you think of numbers which are greater than or equal to 8, less than or equal to 10, and are whole numbers? Well, 9, any others? 8 and 10. So, only possible solutions are t equals 8, t equals 9, t equals 10. Now let's talk about what each one of those means. If t equals 8, how many of type A do we have? Well, we have negative 8 plus 8, which is no planes of type A. How many of type B do we get? We have 20 minus 16, so that's 4. How many of type C? Well, 8. If we have t equals 9, negative 8 plus 9 says we have 1 of type A. 20 minus 18, 2 of type B, and then 9 of type C. And then if we have t equals 10, negative 8 plus 10 says we have 2 of type A. 20 minus 20 says we have none of type B, and 10 of type C. So, if we want 12 planes, and we want to have combined 220 passengers, we have 3 possible configurations. Now, we're ready to answer the question. We know there's 3 chances here. We have, well, not 3 chances, 3 possibilities. We want to know what combination will minimize the cost. So what we have to do is say, okay, for each one of these, we just have to figure out how much does that configuration of planes cost. That just gives us 3 things to check, and then we're good to go. Now let's take advantage of something. What do all of these figures have in common? Hint, I'm underlining it. The thousands, right? So I really don't have to run and do the full numbers here. So the cost will be, if I just think about it in terms of in thousands, sorry, that's very sloppy handwriting, but that says in thousands. Pretend like you could read my handwriting. Sometimes I can read it. It would be 8a plus 15b plus 20c. Oh, not, I read the wrong numbers, sorry. Let's try that again. 8a plus 14b plus 16c. Okay, so for the first configuration, we would get 8 times 0, 14 times 4, 56, 16 times 8. Oh, why am I hesitating? That's a beautiful number. That's 128. And if you add these up, you get 184. 184,000 per month. For the second one, you'd get 8 times 1, which is 8. 2 times 14, which is 28. And 9 times 16, which is, I know what you're thinking, gross. A little bit of accounting humor, right? So 144 is a dozen, and a dozen is also known as 1 gross. Okay, all right. It was funny back in the day. 8 plus 28 is 36. 36 plus 144, 180. Okay, good. Last one, 2 times 8 gets us to 16. 0 times 14, that's 0. And 16 times 10 is 160, giving us 176. So which configuration is cheapest and suits our needs? The last one. It's the smallest number. So we should get 2 planes with the 10 passengers, or I guess we could call them 10 passenger planes, and then 10 planes with the 20 passengers. And there we go. All right. So this is also a problem from the book. All right, any questions? Okay. So in the last few minutes, we're going to talk about matrices. The good news is we're not going to do augmented matrices, they're just matrices. And we say, okay, rays of numbers. We're going to do the following. We're going to talk about today addition, subtraction, comparison, and scaling. When I want to do addition, subtraction, comparison, you must be the same size. The reason it has to be the same size is you have to work entry by entry. If you have different sizes, then you can't work entry by entry because there's nothing, one of them will have a piece that the other one doesn't. When I talk about comparison just says, when is matrix A equal matrix B? And it just says, check if all the entries are the same. That's what I mean by comparison. So, right now, the logical thing is what you think should be true. So we have some examples here. I want to add these two matrices together. So, I have said, add entry by entry. I start with 2 matrices, 2 rows, 2 columns. I'm going to end up 2 rows, 2 columns. How do I find this upper left entry? Add the 2 upper left entries there. So, 3 plus 5, 8. 7 minus 2, Right, 7 plus minus 2, 5. 1 plus 1, 2. 4 plus 6, 10. All right, just add up entry by entry. Subtraction, just like addition. Here we start with 3 rows, 2 columns, 3 by 2. So we're going to end up with 3 by 2. Just subtract. 1 subtract 2, minus 1. 3 subtract negative 4. That's really 3 plus 4, 7. 2 subtract 1, 1. 5 subtract 3, 2. 0 subtract negative 2, 2. 6 subtract 2, 4. So that's adding, subtracting. You can scale. To scale, you multiply every entry by the number in front. So here, this is our scaling factor. Often we just use a lowercase letter. This is our matrix. Usually we use an uppercase letter. So I'm multiplying every entry in the matrix by that number in the front. So everything gets a factor of 3. 6, 3, 12, 9, negative 15, 18. Scaling does what you think it should do. And you can combine. So I can scale and add and subtract. So if you work through this, this will become 2 plus 3 is 5. 6 minus 3, 3. 8 minus 9, negative 1. And 4 minus 3, 1. Now here's the nice thing. Because we're doing this entry by entry, we inherit beautiful properties. If I'm adding matrices, it doesn't matter which order I add. A plus B is B plus A. I can take A plus B, add that, then add C. Or I could add B plus C and then add A. There's something called the zero matrix. And if you hear the word zero matrix, you almost instantly know what it is. It's the matrix with zeros. And if you add a zero matrix to another matrix, it doesn't change anything. Just like when you add the number 0 to a number, it doesn't change anything. It's still the same matrix. And we have some basic distributive laws. And if we multiply a matrix by 0, we get the zero matrix out. So lots of beautiful things happen. Now we're just about out of time, but you can solve. So you could say, hey, if I have a matrix plus a matrix of unknowns and I want to get 2, 4, 1, 7, you just think entry-wise, right? In the first entry, you want 3 plus W to be 2. What does that? What, when you add something 3 plus something is 2, what's our something? Negative 1. And you just go through. 1 plus something is 4. 3. 4 plus something is 1. Negative 3. Negative 2 plus something is 9. Sorry, is 7 is 9. And really what you can think of is you can think of it, oh, just subtract that across. So, okay, good. This is easy, right? Entry by entry. Just a word of what's coming next time. Addition was great. What should we try next? Multiplication. It's going to get weird. So come next time. All right, have a good day.